All right, back to easy physics. This time we're doing thermo. When a system is taken from state A to B along the path ACB, shown in the figure below, 70 joules of heat flows into the system and it does 30 of work. All right, let's draw a picture here. So we're going A to C to B, boom to boom. Okay, so Q is equal to 70. This is why I'm writing this. And W is equal to 30. Awesome. Okay, so now we're looking at question A. When the system is returned from state B to state A along the curved path, which is this one, in case you weren't sure, 60 joules of heat flows out of the system. So Q is equal to negative 60. We're talking in and out here. We're going, okay, does the system perform work on the surroundings, or do the surroundings perform work on the system? How much work is done? Okay, so here's what we're thinking about here. So if we make this is a loop, right? See how it makes a triangle kind of? So whenever you're back to the same place, you have to be in the same situation. Okay, so let's talk about the red stuff. So 70 joules of heat flows in, so we go up by 70, and then the system does 30 of work, so minus 30. So that means that for this situation, we're up by 40. Spot B has 40 joules more than spot A does for internal energy. Okay, so when we're talking about going back, so we lose 60 joules, all right, flows out of the system. All right, so what's happening here? So now we're going to do minus 60 joules because we're losing, flows out of the system, and then we have a W, so plus W. We're solving for that. This has to equal 0 because all of this has to go full circle here. All right, so 70 minus 30 minus 60. So the W is going to equal what? To make this all add up. So 70 minus 60 is 10 minus 20. So W is equal to 20. So far, so good. Are we okay with that? So what does that mean? That means that the system has, so we know it's 20, but which direction is it? Is it the system doing it on the surrounding or the surroundings doing it on the system? All right, so when we're going back, we have to lose minus 40 joules, okay? Now, if we're, because we went up by 40 going red, so red is plus 40. We gained 40 joules this way. We have to lose 40 joules this way, okay? We lost 60 joules from heat. So that means we have to gain some work to make sure we land on the mark. So that means that the system didn't do work, but the surroundings perform work on the system. Okay? So the surroundings do 20 joules of work. All right, that means the system gains 20 joules, or the system gains, or does negative 20 joules. It just depends on if positive, negative means in or out. But the surroundings do 20 joules of work. It's the end of the day thing. If the system does 10 joules of work, and going to from state A to state B, along path ADB, so when we go this direction here, the system does 10 joules of work. So work is equal to 10, we'll say by system. I don't know, just so we don't have to worry about this ambiguity at all. It's not ambiguous, it's just annoying. All right, does the system absorb or does it emit heat? Okay, so we still have to gain 40 joules. All right, so we have to be 40 joules up by the time we get to the end of this purple road. Now we lost 10 joules from work because we did work. This means that we have to absorb heat. How much heat do we have to absorb? Well, if we just absorbed 40, we would have lost 10 from the work. So we have to absorb heat for 50 joules because 10 of those are going to get lost from work and go somewhere else. And so if we absorb 50, we'll be 40 up like the goal was, like we did with the red path. Okay, so now let's look at the next one. If UA is equal to 0 joules and UD is equal to 30 joules. All right, so this is talking about internal energy. So if we call this 0 and we call this one 30, determine the heat absorbed in the process dB and AD. Okay, well, let's do AD first. Sure. Okay, so we're talking about the heat absorbed from here to there. Now, what is significant here is that this purple road that I just covered up a little bit does 10 of work, okay? Now, all the work is going to be done here. You can't do any work on a vertical line, all right, because there's no area underneath it. So that means that this guy has 10 joules work by the system from there. Okay, so if we're going from A to D along that green line right there, that means that we have to go up by 30, but we're going to lose 10, so the heat absorbed is going to be 40 joules. Now, for the second half of this, we'll use light green here. For this side of it here, this guy right here is at 40. We know that already. So A to B, hold on. So we just did A to D, sorry, equals AD. So now we're doing DB, which is the light green. So we're going 30 to 40 here, this light green path. So we need to go up by 10. How much work is there? There's no work. So anything you gain is going to be all internal energy here. So it's just going to be 10 joules for D to B. Sound good? All right, perfect. So we've got one more part here for the process A, D, B, C, A to D to B to C to A. So we're going around the circle here. So we're going this way. Okay, identify each of the following quantities as positive, negative, or zero. All right, so if I'm for work, remember work is the same thing as area. So when you're going A to D, when you're doing this guy, you have this much area underneath your curve. How much is that? It's 10. We figured that out from the other one. Now, this is 0, that's 0, but this one is going to have more area. And since we're going left, it's going to be negative. So work is going to be negative. Okay? I'm going to jump to over here. For a loop, your internal energy is always going to be a 0 change. Whenever you make a full loop, you have to be back to start. How much did your internal energy change? Well, it didn't. It always ends up the same when you make it back to start. So now, let's think about our first law of thermodynamics. So delta U is equal to Q minus W, right? So internal energy change is the heat in minus the work done. Well, if your bank account stays the same, for the full loop, your bank account stayed the same, but you had negative work, that means that you have to have the Q to counteract that. All right? So that means the Q, well, let's see here. There is one hiccup here. So this is heat in, and this is work by. Now, in reality, they want you to do this because they want you to work on instead, okay? Which is annoying. So, but it's okay. It's gonna be okay. So, because this is negative, right? So the system is doing negative work. All right. All right. So we know that the work on is negative. All right. So what that means, all right, since the area is below, that means that there's no work that this system does. It's just work on the system, which means that work on is happening. So work on is going to be a positive value here. Okay, this is going to be positive. It's positive because you have negative area, right? Because the area refers to work by the system. Since the negative of the area, you have positive work on the system. This is why I really hate these specifications. Okay, now since this is positive, that means Q has to be negative, all right? Because it has to add up to 0. That's it. That's the thing. All right, let's look at the next one. Hopefully we can do better, eh? Looking at this one, we got a 0.4 mole sample of an ideal diatomic gas. Ew. Undergoes a slow change from state A to B to C. A to B to C. Boom, boom, boom. And then back to A along the cycle shown. So nice of them. All right, 0.4 moles. I'm just going to write that before I forget. Okay. Path A to B is an isotherm. Nice. And it can be shown that the work done by the gas as it changes isothermally from state A to B is given by this equation. Nice. Do you smell an integral in there? Anyways, what's this temperature of this state A? All right, let's look at state A. All we're going to do is do some PV equals nRT here. So for state A, we'll do the first one more thoroughly. PV equals nRT. We know the pressure at state A. The pressure of state A is going to be 2.4. We know the volume of state A. It's going to be, well, we've got to be careful. It's times 10 to the minus 3. Oh, got to be careful because this is times 10 to the 5. So we're going to have 12 times 10 to the minus 3 equals n, which is 0.4, times r, which is 8.31, times t, and we're just going to solve for t. All right, so t for the first one is going to be 870 Kelvin. Now let's do the same kind of thing for state B. This side's going to be the same. It's just going to be changing this side here. So we're going to have for state B, it's going to be 0.6 times 10 to the 5 times 48 times 10 to the minus 3 is equal to 0.4 times 8.31 times t. So solving for t on this one, you're going to get 870K. I know what you're thinking. It's the same. And yes, it is the same. You know why it's the same? Because it's an isotherm. So they're going to be on the same temperature. I didn't think of that until now. Anyways, let's do the next one, state C. State C is not going to be the same, promise you. So we're going to have that lower pressure, so 0.6 times 10 to the minus 5. And then that volume of 12 times 10 to the minus 3 is equal to 0.4 times 8.31 times T. What's the temperature going to be? Temperature is going to be 220 Kelvin. Nice. So that's all you have to do for that one. So now for this one. In order for step AB to be isothermal, the gas must be kept in thermal equilibrium with its surroundings at all times. Yeah, same temperature. Because heat flows spontaneously from hot to cold systems, this implies that there is no heat flow during step A and B. During step AB. Is there heat flow? Yes, there is heat flow. There is heat flow. Okay, how do we know that? We know that we're going this way. There's area underneath that curve, right? We know that because it's doing work, because it tells that. So there is heat flow. Since W is positive, that means, well, since W is positive and isothermal. Now, what does that mean, isothermal? Isothermal means that delta U is equal to 0, because for a gas, the internal energy is all about the temperature. Okay? That's the whole shebang. So you have two situations when you have delta U equals 0. One is if it's a full loop, and the second is if it's an isotherm. All right? Now, part of this comes into play because the same point is on an isotherm with itself. So it's kind of silly like that. An isothermal, so delta U equals 0, Q cannot equal 0. Right? So since it is doing work, it'll have to absorb the heat. It's just done so slowly that it has a chance to pick up the energy at the same rate that it's leaving. And you have to do that slowly. That's why it has that word in there, slowly somewhere. I don't remember. Slow changes. Okay. So that's what they're talking about there. So how much work, WAB, is done by the gas during the step AB? Well, we have this formula. All we got to do is plug it in. All right, so let's do that. So W is equal to negative N. Oh, let's just plug in the values. Negative times N, which N is 0.4, times R, which is 8.31, times T, which is the temperature. It's going to be these temperatures here, because it doesn't matter which one, they're the same. 870 times the natural log of volume B, which is 48 times 10 to the minus 3, times 10 to the minus 3, divided by volume A, which is 12. 12 times 10 to the minus 3. And the minus 3's cancel out. The 10 to the minus 3's cancel out. Okay, so all you got to do is typey that in, and you are going to get negative 4,000 joules. So nice. Okay. So what that is talking about is that is using that equation, isotherm, the work done by the gas as it changes isothermally. So nice. Okay. From A to B. Yeah, all right. So what is the total work done over the whole cycle? All right, so we know the work done there. All we have to do is figure out this work. That's the only other place with work. And that's a rectangle. We can do that easy. So your area of a rectangle, your height of the rectangle is going to be 0.6. What's your width of a rectangle? It's going to be 48. take away 12, which is going to be 36. Oh, I forgot that scientific notation. All right, so it's going to be 0.6 times 10 to the minus 5, 10 to the plus 5, times 36 times 10 to the minus 3. So we're going to multiply those guys together, and we're going to get 2,200. All right. Now, so what we're going to do is combine these two together, add them together. We don't have to worry about this vertical step here because W is equal to 0 for stuff like that. So add those together, and we get negative 1800 joules. And that is it. Ta-da! Hopefully you had fun with thermo. We'll see you tomorrow. Like and subscribe.